Let's start. So today's lectures will be about mesh generation, or how to generate a lot of connected elements, not doing it by hand. So when we get to more complex problems than we have seen before in this course currently, with the 10 or 15 elements, when you have really large problems, you need to generate meshes with a high density, and it's very hard to do that by hand. So we need to kind of have some kind of algorithm that helps it out to create this mesh. And there are many algorithms that use geometric description as input, which we'll be using this course as well. And these algorithms, for those algorithms, you can actually define different constraints or boundary conditions for the mesh. So you can set, for example, that I want to have a maximum area of the elements or maximum volume. You can also set the maximum elements on a different on a specific geometric entity. So say a line, I want to have 100 elements on a certain line, and the mesh generation will kind of create that. In many of these algorithms, you can also take the results from a previous calculation as input to refine the mesh. For example, if you have high stress concentrations, you can use that as an input to refine the mesh and add more elements at those points. There are essentially two basic mesh generation strategies. So you can have structured mesh generation, which is where you have a rule that defines the mesh, usually with some kind of coordinate system that specifies rows, columns of elements. But there is kind of a rule that determines every element. And you can also, by specifying a certain row and column, you can get to the exact element. The second strategy you can use is unstructured mesh generation. And then you have a specific algorithm that fills your domain with elements. So essentially you have your geometry, and then you have an algorithm that kind of, using a specific kind of strategy, fills the domain with elements. Usually these algorithms are limited to triangles or tetrahedral elements. But many of these many of these mesh generation, they start with a triangular mesh, and then they combine the triangle to a quadrilateral element or similar. So you can kind of start with a triangular mesh and then use that to kind of generate element mesh for other types of elements as well. This is an example of an unstructured mesh. So here you can see that you have a geometry, and then you have basically you have poured out the elements inside the geometric boundary condition. So the algorithm will fill the mesh with points and then connect them together to form a mesh. And usually these mesh algorithms start from the boundaries and move in. You can see the kind of wavefront here on the mesh here, that it moves in and then so that it completely fills up the geometry. On the right side here we have a wing in a fluid domain. That also is a structured mesh, and here you can see that the mesh has been refined around on the wing edge here. So there are some kind of rules here that says that we need some number of elements on the wing edge, so to speak. Structured mesh is here you can see that you have some kind of rule that determines how the elements are laid out in the mesh. So in this case here you have here 6 elements on this size, and then you have a coordinate system here. There are columns here with rows. Even if there are bent here, it's still a structure where you can identify. There's a rule to kind of calculate the position of each element. And here's more simpler forms. Here you have a block divide it in rows, columns, and depths. Both in all dimensions. And here you can also specify rules here with. So you want to have more elements or higher density in the middle here, and so you can concentrate on it. So there are some rules you can set to kind of, even if structured method, you can refine the mesh in certain ways. But even if you have structured mesh generation, you can actually create quite complex meshes by using quad elements, super elements in this case. So here's an element with 1, 2, 3, and 4 sides. And you can have curves on each side of these super elements, and then it generates the elements here in the super domain or super element. And then you can combine them together to kind of create this complex mesh. In this case, it's a tunnel here, and there is a symmetry line here. And these methods are kind of good to kind of you have very great control over the mesh generation here. So it's easy to say I want more elements here, and then this will add elements on both of these super elements, and you can refine it in this direction here as well. It's also very quick to kind of find elements. If you have an unstructured mesh, you usually have to have some kind of search algorithm to find an element in the topology. With a structured mesh, you can very easily go directly to an element and calculate its value. You don't have to search your topology for the element. Excuse me. In this course, we will use a mesh generator called Gmsh. And this is actually much more than just a mesh generator. It's actually a graphical user interface as well as a mesh generator. We will mainly use it as the mesh generation tool. So because the user interface is extremely complex to use. So it's a mesh generation application. It contains, so you can actually do both pre and post processing in this mesh generator as well. And it can generate basically any kind of mesh you would like to have. So it can do both structured and unstructured meshes. And it uses a geometric description as input, which can consist of lines, circles, splines, and surfaces. And geometry is described in a special language. But we have built, to make it easy to use mesh generation in Calfem, we have built-in routines to use Gmsh, the underlying software, for generating mesh automatically. So you don't have to know much about the input language for Gmsh. You can use the commands provided by Calfem to generate the geometry, and it can also generate the mesh automatically. So two modules are used here. So one is called Calfem.geometry for describing the geometry of your structure, and Calfem mesh for running the mesh generation. So these two are the most important one. And the geometry is described in a special class, an object called geometry. So you create this geometry object, and this will contain all the nodes, the lines for the geometry. And then you pass this object to the mesh generator, which takes that object and generates the input necessary for Gmsh. And then from this function, you will get all the conventional input data for Calfem. So you will get the topology, you will get the coordinates, and so on. So you can use your basic what you develop in the current worksheet. You can also do for larger problems. So if you have the same kind of structure of your solver, you can just take the input that comes from the mesh generator here and run it, use it directly with Calfem. Yeah, the results are arrays that can be used by Calfem directly. I will do a short example here to illustrate how you do the meshing in Calfem. So this is a geometry here for a typical groundwater problem, for example. So you have a domain here, it's W wide, it's H high, and then you have a slot here that is D in depth and T wide here. And then we have nodes here, 0, 1, 2, 3, 4, 5, 6, and 7. And we have edges here or lines that 0, 1, 2, 3, 4, 5, 6. So we will create a parametric model here. So we will specify all these values here as variables, so you can change it. So you can, the geometry will be generated from these variable parameters. So what we need to do first in our code is to import our modules. So Calfem core is the element routines. We needed geometry here, and we do call that CFG. And we have Calfem mesh, CFM. Visualization here for visualizing, we do CFV. Calfem utilities as CFU. And then we also need NumPy here, so we do that, import NumPy as MP. So now we have everything to start implementing our model. And then first we set up our problem parameters. So we have W, H, T, and D here. So we do it's 100 meters wide, 10 meters high, and we have thickness of 1, and then we have the depth is half the height here. We create an identity matrix here, D. We don't specify any values here, but this is just kind of illustrating. And then we define a geometry. So the first thing we do is create the geometry object. So this is a class, as I described earlier here. It's a kind of template for creating an object. And this geometry class describes how to create a geometry object. So we create it like this, and then we get a J here, which is our geometry object. And using this J here, we can define our geometry. So in this case, we do G.point, and then we just add our coordinates for our points here, and using the variables we defined before here. So it's the entire geometry is described by parameters. So then we have our points. So the next step is to add our lines. It's called spline or line. And if you just only specify 2 points in the spline, it will be a line. So G-spline from node 0 to node 1. And then spline from 1 to 2, 2 to 3, 3 to 4, and so on. So this defines the geometry topology. And then we can also, to be able to identify lines when we want to apply boundary conditions, we need a way for us to extract certain elements or nodes, and that we can do by specifying markers here on the line. So we can set different identifiers here. It can be any number, and that number we can use them to extract degrees of freedoms for our boundary conditions. And finally, we need to define a surface here. So the surface we define by all the lines here, 0, 1, 2 to 7 here. So that is our kind of surface we want to generate our mesh. Yeah. So next step, we will do a mesh generation. And here you do element type equals to 3. That is the element type we want to use, and I think that is a quadrilateral element. And then we have the element size factor here is a variable that determines how large elements we want to generate. And you see also here we give the geometry to our mesh generator when we create it, and then we specify our element type and also the number of degrees of freedoms per node. So as this is a groundwater problem, we only have 1 degree of freedom per node. So that is also, we also need to specify that. And then we create our mesh. So mesh generation.create, that will initiate mesh generation, and it will return a coordinates array, an EDOF array, a DOFs array, which is the degrees of freedom for each node, each coordinates, sorry. And then a boundary DOFs here, that is a structure that specifies the degrees of freedom for each markered domain. So if we have 80 here, you can go in here and access the degrees of freedom on that boundary is contained in this special array. So what we do then is first we need to figure out how many degrees of freedom do we have in our problem. So we do that by specifying n-dofs equals to mp.size. And in this case here, this is the number of degrees of freedom we have, is the size of this array. We will extract element coordinates, and we do that using the chord extract command here. And then we do edof as input, chord as output, and then dofs here. I have a question here why the markers equals 80, 90. So this is just arbitrary numbers. Usually the markers can be anything, and I usually name them. So I give variable names for constants. So for example, left boundary equals to 43 or something. So they can be anything, but one idea is to give them names and use them as markers in the code. So it's just an identifier. It doesn't mean anything in the simulation code. And then we create our stiffness matrix like this. And then we do basically what we did in the last lecture here. So we loop over the edof, ex, ey, and then we get to the element topology, the element x, element y, and then we assemble our element here into the stiffness matrix. First we calculate the element stiffness matrix Ke, and then we assemble it into the global stiffness matrix. Boundary conditions, here is where the markers come in. So we need to create the force vector, and then we have to create two vectors for one vector boundary condition to specify which boundary conditions to set, and then a vector for the values to set on that boundary condition. And then we do BC val. So here we apply on the boundary condition, we have to specify as input the BC val, and here is the marker that we want to apply this boundary condition to. In this case, it should apply the value 0 on the marker 80, and then we have to apply the value 90 on marker, sorry, value 10 on marker 90. So this is a special utility routine that helps you apply the boundary conditions. There are some other ones as well, and I would suggest that you read the documentation for the Calfem Python. There is it describes all these different ways you can set up boundary conditions. So solving is just like we did before, A, R, and CFC solvec. And then we apply our boundary conditions here as input. We extract our element displacements. And the same thing here, we loop over here and extract our boundary condition, extract our element forces, and add them to the result vector max flow here as well. Then we can do some visualization here as well. So draw geometry J, draw element values. I just realized now that we are using somewhat old syntax. There is new syntax here where it's called draw underscore element values underscore. But look at documentation and examples. So this will draw the element values in the elements. You can draw the mesh, and you can draw the nodal values at the nodes. You can add a color bar, and then here show and wait will stop the program and wait for the visualization windows to be closed before continuing. So this is how it can look. So this is the draw geometry command. Just shows the geometry like this, and this is the nodal values, and here is the flows in the element flows. Which is drawn by draw element values. So it colors the entire element with a scalar value. So that was basic introduction to this. So now I will do another example here. Let's see if I can. So I will do an example in Spider here that is a bit more complete. So this is an example where we have a element mesh that looks something like this. I'm not good at drawing here. So this should be half circles here. There is a load applied here. I think it's applied on the entire side here. And then it's fixed here. So that's basically it. So the geometry will describe by lines here and then a semicircle curve here, a line, and so on here. So let's see if we can find my. So this is a more longer example here. You can see here that we have our all the modules that were required for running Calfem. We also use NumPy here. We had math here for square root calculation here. Not strictly not necessary. We could use the MP function as well. First thing we do is we just define our problem variable. So T, the Poisson's ratio, and Young's modulus here, and then P type 1, that is plane stress. And then we have element properties. We give that as a P type comma T, so that is what the element routine wants. We create our constitutive matrix here, D, P type E comma V. So these are basic values here. And then we, as we said before, we create the geometry here. And then we do some, this is not two parametric function here, but we define our points. And then we define our splines here. And then we do some splines here. And then we also have some markers here defined here, elements on curve. And then we also specify IDs here for the different, this is the right-hand marker on the side. So this is the right side that we will apply a load, and then this is the line on the left. So we have 7 on the right and 5 on the left. And then we have some arc. So this is the really complex geometry here. And then we just created a structured surface here like this. So this is a structured element mesh generation. And then we create our mesh generator here. So in this case, we have mesh equals to Gmsh mesh, and then we have input here is our geometry, element type 3, so it's a quadrilateral element. DOFs per node is 2, so every node has 2 degrees of freedom because this is a stress problem. We run our mesh here, so EDOF, DOFs, BDOFs, element markers, mesh, so, and then this will create the actual mesh. Here we assemble the system matrix here, EX, EY coordinates, and then we loop over all the elements here and assemble them into our global stiffness matrix. We create our force vector. We create boundary conditions here and the values for boundary conditions here. We apply boundary conditions here at element 5, and we specify that both degrees of freedom should be 0. So in this case here, 0 and 0. And we apply a force here on the boundary ID 7 with a certain force. And we solve our equation system here. And then we calculate our element forces. here and store the von Mises stresses in this list. And then we run our visualization here. So, and if we run this now, let's see here if I just, it will run in the current interpreter here. And this has an effect if you just run your program directly in Spider. You see it stops here, but nothing happened. But it's not true because the plots actually happened here. So you have all the, so this is the geometry, mesh, effective stresses, and then also the displacements here. If you want to run them where you can have a bit more control, you can run your code, instead of running it in this interpreter here, you can go Tools, Preferences, Run, and then you say Execute in External System Terminal. Okay, and then we run again. And then you see you get a window here where the code is running. And when the plots come up, they come up as separate windows here now. So here we can zoom out, or zoom in, sorry, and look at our geometry. We can look at our mesh, like this. So now I see this is a structured mesh consisting of these super elements. And we can look at the effective stresses here. And our displacement like this. So you can control this using the preferences here. You can switch between these ones here. You can also, for every file you have in Spider, you can set the configuration per file. So if you go in Run here, configuration by file, you can set the settings for the file you want to run. So except if you want to run in a dedicated console, you set it here. If you do this one, it will create a new console in Spider here. And that could be a good idea because if you execute in the current console, all the data and variables you create will still be left over from the last run. So when you're debugging your code, sometimes it hides errors when variables are there already. So if you want something that for each run that is clean and empty, you can do execute in dedicated console. And then we can do run it here again. It will create a new console here, basically starting Python from scratch and running it inside here. Now there is no existing variables, it's completely empty. And you see here also now it creates the plots here in this part here. And when I run it again, it will create it will kind of clean this one here again. And there are some other options also that you can use. For example, remove all variable for execution. That can also be a good thing to do. So if you're debugging your code, this will clean out all the variables for you. So we can see here if we look. So now I have all the variables here. And if we run it again, it will clean all the variables before running, which can be a good idea if you're debugging your Python code. Okay, so let's see here. I would like to do Want to talk a bit about how your project will be laid out and the thought. So if you have a finite element solver, you usually have your input. This is not so. I will try to. No. And then when you have input, it goes to a solver. And then the solver generates output here. In our program, the input will come from an input file. Output will be also generated to either visualization windows or it will also generate files here that we can visualize. So in this case, it will generate something called a VTK file here. We'll go through this later on. So this is a visualization toolkit file that can be read in a special visualization environment called ParaView. And this will also be generated from the output here. So this is a general overview of the solver. And also the input will also be from, you will have a graphical user interface here. GUI like this. That will generate this input as well. So it will read and save this input file. So the code in itself will be structured. So this is the conceptual model of the program. The code will be focused on, when you do the worksheets, on different classes here. So you will have one class that is input data. I'm not very. Okay. We will have a solver class. And we will have our output data class. And the solver will have, so what you do is that the solver will be given an instance of this one here. So the solver will you give a reference to the input data. Same thing with the output data. And you will also have a results class. And result will store all your so no, not the results. It was report. So report will also have access to the input data. And output data. So report will take the results, write a report from the input data, and also present the output data. There will also be a visualization here class. Okay, not so very, but that will also reference this input and output data. So this is the idea that you have this kind of information container. So you have the container that contains all your, describes your problem with the geometry, with your attributes like material properties. And then you have output data is the result from the calculation. And the solver kind of doesn't store anything. It just takes these input, combines them, and generates output data. And then the report will take the input to generate the report. The visualization will take the data in input data and output data and combine that and create a visualization. So that is the kind of main idea. So using this concept of input and output data objects, you can actually very easily create multiple sets of input data. And for example, to do a parameter study, and I will show you this shortly here. And you can also have so for each parameter you solve, you also have an output data set. And then you store them, for example, just in Python lists, and iterate over these and solve them very quickly. So it's basically just a question of creating a new input data, modifying one parameter for each of your parameter sweep, and then looping over and solving, and then you have all your output data stored in a list which you can plot or do a diagram. So this is the high-level idea of this computational code. So let's see here. So if we look at, this is an example here from the finalized project here, from the worksheets. So you can see here, this is my stress model. I have all the classes that is required for my model is contained here. So I have a input data class, I have an output data class, I have a solver class, I have a report class, and a visualization class. And if you look at the input data class, we look at the solver class. The input to solver class is input data, output data. So here it sets its internal attributes here is the input and output. So when you solve the problem, it will take the input here. You can see the input here is taken from the input data, stored in temporary variables here inside. And then when the calculation is done, it will store all the results here in the output data variable. So basically, the solver doesn't store any input or any output. It stores those in the input data object and reads it from the input data and stores results in the output data. And then the report, the same thing here. It also has the input data here and also has the output data here. And then it creates a report on the input data here and also on the results, combines those. And the same thing, the visualization here also has the input data and output data. So input data and output data. So if we, I want to show you if I create a, and then we do so if I run this code now here, it will create an input data instance, an output data instance, and then I will pass those over to my solver, and it will execute those. So let's see what happens here. First, it creates the meshing here. So the meshing is done internally in the solver now. There's no mesh, so it's completely automated here. I think it's already done here. Like this. So I'm just going to stop the code here before I execute the solver here. set a breakpoint here, and I will run using the debugger here. So now you see it stopped here, and you see I have two variables here. And we can look at the input data here, and you can see here that the input data is a quite complex object. It has a lot of things. So it has the elastic modulus, you have the A parameter, B parameters, you have the boundary conditions, a lot of other things here. So it's basically your data container, which you pass over to your solver. Same thing with output data here. Now it's probably completely empty because it hasn't been run. The solver hasn't been run. So if you run the solver now, we step over here and we execute the solver. Let's see if we have. Okay, let's see if it's done. Yeah. So now you have the output data has solver has finished, and now you see here that the output data is filled with data here. So you have your displacement vector, you have the coordinates, you have ED, ES, ET, and so on. So you have all the data for this calculation. So what you can do now very easily is, I stop the button. So let's see here, instead of having input data, a single input data and output data, I create two lists. See, I start from the beginning here again. I create a input data list. Just do like this, and do an output list. So just two empty lists, which I will use to store the results. So let's see here now. I want to simulate my height of my model here to go from 0.1 to 0.2. So I create a param h equals to np.linspace, going from 0.1 to 0.2. I say we do it in 5 steps, so not too many. Loop for h in param h colon, and then we create an idata here, which is input data. We modify idata.h, which is a attribute of my input data, set it to h. We need an output data. And then we create a solver. Actually, we could create the data, it's more efficient. We create a solver outside here. Solver equals to solver. We just provide none, comma none here because we don't have any input parameters for the input here. And we do solver dot input data equals to idata. Output data equals to. And we do solver dot execute. And we say here just to print out what we're doing, print solving for h equals to h. So let's see what happens here. Just going to make sure I did the break. Remove all variables here, executing current console. Okay. Now I say source for 0.1 here. $0.125. I think we'll just one more to solve here. This is the final one. So if we now look here, we have our input data list. Okay. Oh, I forgot one thing. I didn't append them to the list. Kind of stupid of me. Okay, of course we have to store them in the list, otherwise they just get forgotten. So now we did a lot of calculations for nothing. Okay, we do 2 instead here, just to make it quicker now. So we run it again. So now we have a list here. So you can see here that we have an input data list and we have an output data list. And we look here, we can see that we have one input data here, one input data here, and you see that the H parameter is 0.2 here, and the first one is 0.1, 0.1 here. And we have one output data for each of the runs here. So using objects and clauses like this gives you a very powerful tool to do very complicated things I mean, this is let's see, 20 lines of code or something like that. You just create an input data here. Of course, the input data is kind of complex in itself. It has to be defined. But if you have a model and you want to change a parameter, this is way you can do it very easily. And this is what you're also going to do in the coming worksheets as well, that you will do a small parameter study with your data. And the idea is that you create input data sets for each of the simulations, pass that to the solver. It knows how to handle that. So I actually don't have much more today. We have an exercise in the afternoon at 3:15. I will be there and also Karin. So do you have any questions so far, or is it? I know there's a lot of things directly here, but I think it's there is a lot of documentation available on the web pages for this. All the examples in Calfem, I will also provide you with a link where you can download all the examples here. So I can open here. So if we go to Calfem Python here. So this is the code repository for Calfem. And in the examples here section, you have multiple examples of different kind of finite element examples here. And all those that have the EXM prefix, those are mesh generation examples. And the suffix here, MPL, stands for matplotlib. So those are to execute, those don't require an extra install. So those are the easy ones to use. So use those with _MPL. So they're available. You can look at them here. So if you go exit 10, you see you have the code here, and you can download and copy here. So that could be a basis for your own code. So you can in your worksheet you can look at this and see how it has been done in the different examples here. So use the code. I will add a link here as well in the web page so you can use those. You can also see the Calfem Python here. In the Calfem here you have all the modules available. You have the core module here if you're curious about the code. So here are all the element routines implemented. So that was what I wanted to talk about today. So I will try to generate a video from yesterday's lecture today. It should be available in the afternoon, and then tomorrow or something you will get this lecture as well. So if you don't have any, so I will provide the links in the web-based Canvas part. So you will get the links for this right now. Okay. Any questions? Otherwise, we have a lecture in the afternoon where you can ask all the questions you want. So see you in the afternoon.